So hello everyone. In this tutorial we are gonna take the question minimum height trees of LeetCode. Okay. So as given in the question, you are given a tree having n nodes and n minus 1 edges. Among all the n nodes given, you have to choose any of them as the root of the tree such that the height of the entire tree formed is minimum possible. So let's visualize this question a little bit more. So let us take example with this tree. Okay. So we have 4 nodes here, 0, 1, 2, 3. So suppose I take root of the tree as this node. Okay. I root the entire tree at node 0. Then the distance from this node 0 to node 1, I get it as 1 edge. Similarly, I can say that okay, distance from node 0 to node 2 and 3, they lie after traveling 2 edges. So as we know that from root we need to go to the deepest node, and that how many edges we have traveled in between, that constitutes the height of the tree. Okay. So okay, the deepest node, if we root the entire tree at 0, is coming out to be both 2 and 3. Okay, so the maximum distance we are getting from here is 2. So the height of the tree we get if we root the entire tree at 0 is 2. Okay, similarly we can see that if you root the entire tree at either of nodes 2 and 3, also the height of the tree comes out to be 2. Fine. Now see, if we root the entire tree at 1, at all the other nodes that we have 0, 2 or 3 lie at a distance of just 1 edge. So it's better for me to root the entire tree at 1 so that I get minimum height that is possible for the entire tree to be 1. Okay. Now let us take another example. Okay, we have total of 6 nodes here. So suppose that I start with rooting the entire tree at 0. Okay. So if I root the entire tree at 0, what is the maximum distance from 0 to any other node that's possible? Okay. So if you form the path from 0 to 5, okay, this is the longest path that we get here. Okay. So maximum distance that we get if we root the entire tree at 0 is 3. Okay. Since 5 is the deepest node here, so the maximum distance we can travel from 0 to any other node is 3 edges. So minimum height that is possible here if I root the entire tree at 0 is 3 units. Similarly, if you root the entire tree at any of the nodes 1 or 2, okay, you will get that okay, from 1 and 2 both, I require 3 edges to be traveled to reach the deepest node 5. Okay, again 5 is the deepest node if we again consider 1 and 2 as my root. Fine. Now let us consider 3 as my root. So from 3, I require distance 1 to be traversed to reach node 0. Similarly, to reach node 1 or 2, I require only one edge to be crossed. Okay. To reach node 4. Okay, by mistakenly I have said 4. Since 4 is not a leaf node, we don't need to consider that. From 3, if I need to reach 5, okay, we need to cross exactly 2 edges. So the deepest node, if I root the entire tree at 3, is 5. Okay. From 3, the deepest node is 5. So we require to travel exactly 2 edges to reach 5 from 3. So the height, okay, of the tree is coming out to be 2. If I root the entire tree at 3. Now similarly, if you root the entire tree at 4, I require to travel exactly 1 edge. Okay. From 4, I require to travel exactly 1 edge to reach 5. Okay. And rest of the leaf nodes 0, 1 and 2 I can reach by crossing exactly 2 edges. All of the leaf nodes 0, 1 and 2 I can reach after crossing exactly 2 edges. Fine. So what's the maximum distance we are crossing here? What are the deepest nodes for us? They are 0, 1 and 2. Fine. So again the height, if I root the entire tree at 4, is coming out to be 2. Okay. Now again, if you root the entire tree at 5, then 0, 1 or 2, all of these 3 are do require exactly 3 edges to be crossed. Okay. So all of these 3 are the deepest node if we root the entire tree at 5. So again, if I root the entire tree at 5, the height is coming out to be 3 units. So what's the possible answers for me? Okay. in this question both 3 and 4. Okay, both of them needs to be printed. Okay, if I want to root the entire tree at any of the nodes such that the height is minimal possible. Both of them are my possible answers. Here in our previous example, since 1 was the only node from which I am able to cover all other leaf nodes in minimal possible distance. So that's why we have only one answer. Okay, that is 1. So one way to approach this problem is to try at every node the entire tree once, and to check which of my nodes are giving me the least possible heights. Okay, those set of nodes will be taken as my answer and I can just return them. So if I consider each one of them as my nodes, okay, so I have n possible choices and I need to find the height, right? After routing the tree at any one of the n nodes, I need to find the what is the minimal height of the entire tree that's possible. So that will take either a BFS or DFS approach to find the height. Now what we can say is that it takes big O of n time. So big O of n, we have n number of times to perform BFS and DFS because we have n choices of nodes. So what we can say is that the final complexity will be turning out to be big O of n square. Okay. So here see the constraints will be a little bit tight because it's given 2 into 10 to the power 4, the number of nodes. Okay. So we need to think something better. So to solve using the most efficient approach, why don't we think of a generalized node? A generalized node such that distance of all other nodes from it is minimal possible. If we think in these terms, our entire problem is but finding the center of the tree. So at the center of the entire tree, if we try to root, okay, if we try to root the entire tree, then we will definitely find the minimal height possible for the entire tree. Okay, that's guaranteed. Now how to find the center? Okay, so we see here that what's the diameter? Diameter is basically the longest path between any two leaf nodes that's present inside the tree. Okay, so here if we try to find out the diameter 6, 2, 1, 3, 5, 8, this is consisting the longest path. Okay, how many nodes does it have? 6 nodes. Okay, so center are the middlemost 2 nodes here. Why? Because there are 6 nodes, even number of nodes in this longest path or in our diameter of the given tree. So we have 2 set of centers. Okay, why is it so? So let's see that. Okay, if I write it here, if I take 1, okay, if I take 1 as my root, okay, so its deepest node as per this root is going to be 8. Okay, that's at a distance of 3 edges from it. And if you consider 3 as the root, then the farthest node from 3 is 6. This is again consisting of 3 edges to be crossed. Okay, now both of them are possible answers for me because if I choose either of them, I am gonna get my height of the entire tree as 3 units. If either of them I choose as root of the tree. Now if I say any of the nodes in my diameter, let's say doesn't exist. Let's suppose this 8 doesn't exist. Then our diameter turns out to be 6, 2, 1, 3 and 5. Okay, this is of odd. This consists of odd number of nodes here. So we have just we can choose only one node, that is the middlemost node 1. Okay, such that if we root the entire tree here, the farthest node comes out to be at 2 units. Okay, so it's a general observation in terms of finding center of the entire tree that okay, if there are in the longest path, if there are even number of nodes, we have exactly 2 centers, and if the number of nodes are of odd number, then we have just one center of the tree. Okay, so we cannot have our answers more than 2 nodes. Okay, one is the minimum possible and 2 is the maximum possible for any of the given tree that we are gonna have. Now, how do we find the center? Okay, what's the best approach for us? So let us say that, okay, what are leaf nodes of my entire tree right now? There are 4 nodes. Okay, this 1, this 7, this 8, and this 6. Okay, let me visit them at time 0. Okay, at time 0, I have visited 1, 7, 6, and 8. Okay, and let me prune them off. From the entire tree, I am pruning them. What's the identification of a leaf node inside the tree? That its degree is only 1. It has only one edge attached to it. Okay, so if I prune them or remove them from the entire tree, what's remaining for us is, let us see that. Okay, so I've pruned them successfully. Now see, my entire tree is consisting of these 4 nodes. 2, 3, 4, 5. Okay, let me write it separately. Now I can say that, okay, whatever tree is left to me, this 2, 3, 4, 5. Okay, what are the leaf nodes here? Okay, leaf nodes here remaining are 2 and 5. So let me again prune them off, and let me now, whatever are my current leaf nodes, let me visit them at time 1. Okay, at time 1 I am visiting nodes 2 and 5 because after pruning off my previous leaf nodes, the current leaf nodes I got 2 and 5, I am gonna visit them a time later. That is at time 1. I will visit them. And now after I prune them off, I am left with this 3 and 4 only. These are the leftover leaf nodes of the entire tree, and I am gonna visit them at time 2. At time 2, I have visited nodes 3 and node 4. Okay. Now you can see that whatever node I have visited at the end, at time 2, what they are? They are the set of centers for me. Since what entire tree we had was this, right? 1, 2, 3, 4, 5, 6, 7, 8. Now the longest path here is between 1 to 6. So these two are the set of centers for me. Why? Because it consists of even number of nodes, the longest path, and the middlemost 2 nodes that we have are my set of centers. So see, we can visit the set of centers. Okay, if we try pruning off the leaf nodes one by one and level by level, if we from the outermost level to the innermost level, if I travel or traverse the entire tree, I will be able to visit the set of centers that I have at the last time. Okay, all of them together. Let us take another example for a better visualization. So let's take a simple tree here, and again, firstly we are having 1 and 5 as our leaf nodes. Okay, so at time 0 I will be visiting 1 and 5, visited, and let me prune them off. So after pruning them off, I am left with 2, 3, and 4. What's the current set of leaf nodes for us? 4 and 2, right? Let me visit them at time 1 and let me prune them off. Now after pruning them, I will be left with only one node, that's 3, and I will be able to visit it at time 2. So we can see that, okay, the latest time, what node I can visit? 3, and that's the center of the entire tree. Okay, if we correctly visualize this tree, what we are getting, okay, the entire tree has only one path, and the longest path is just one, this 1, 2, 3, 4, 5, and the middlemost node 3 is my center. Okay, this 1, 2, 3, 4, 5 consists of the diameter, and the middlemost node 3 is my center. So let us move on to the coding part and see how do we code it. So let us observe one thing. Suppose that we are given with this tree. Okay, so how the edges will be looking like, the edge structure. So see here, there are exactly n slots. Okay, this particular slot of my 2D vector edges, the 0th slot or the 0th index, determines, has, or rather has, this 0th index element of my edges has another vector inside it, 1 0. This determines that, okay, zeroth node has an edge to what? Sorry, my expectation went a little bit wrong. I was wrongly analyzing there. Let's see how the vector of edges here is represented. Okay, it's given as a 2D array. How it's given? Okay, so it's given as a list of lists. Okay, inside the outer list, okay, there are separate indivisible list, and that has two entities. Suppose that it's given here 0 1, represent that there is a bidirectional edge between node 0 and node 1. Okay, similarly, if it is given 1 2, then there is a bidirectional edge between 1 and 2. Okay, so what how we are going to approach the code? Okay, let's see that. Now before that, let's observe a few things. That, okay, since the edge is bidirectional, that means if one is my node and it has an edge towards another node 2, that means this edge counts to the degree of both 1 and 2, right? So we have to keep that in mind. Also we know that, okay, for all leaf nodes the degree is always 1. Degree is always 1. So let's keep a degree count for each and every of the node. Let's see how we are going to do that. So let me first declare a degree vector. Fine. And that's for n nodes, and individually before calculating everything, before calculating anything rather, the count is 0. The degree count is 0 for any of the node. Okay. So let's first calculate the degree. So I will go to the indivisible list that's given in the edge list 2D vector one by one. So what I am gonna do here, okay, if I am on the ith list of the edge, okay, the edge consists of indivisible list, and that's again enclosed inside an outer list. So individually, if I am on the ith list, then what I am gonna do? How to maintain the degrees for any of the nodes. So the ith list has exactly two nodes. Let me determine them as u and v. Let u stores, okay, what is the zeroth node given here, and v denotes what is the first node given here. Only two is possible. Okay, you can see that indivisible list inside the outer edges list is having two nodes only. Why? Because a single edge can lie between, at most an edge usually lies between two nodes only. So that's why we don't have no more, we have only two nodes for an indivisible list. Now since we have seen that any edge, a bidirectional edge, is counted for both u and v. So what we are gonna do, degree of u we are gonna increment by 1, and degree of v we are gonna increment by 1. Okay, we have done that. Okay, so successfully, if we go like this, we have successfully calculated the degree for each and every of the node. Now I will traverse first the outer nodes. Fine, how I'm gonna do that? So I will be utilizing a queue, and first let me push everything or every leaf node inside the queue. So what I will do, I will just go one by one for all the n nodes, and will check if the degree for any one of them is 1. Then what I am to do here is I am to push them inside the queue. Okay, pushed. Now we have again seen the time concept, right? So let's keep a separate vector of time. And this is again for n nodes. What node I am visiting at what time individually. Let's say all of them I haven't visited till now, and what I'm gonna do is, okay, I'm gonna mark that, okay, since I haven't visited any one of them, let the initial time, okay, let the initial value inside the time vector for each and every of the node be -1. So let us do that. Now at the 0th time, what I'm gonna say, if suppose for all the leaf nodes their time value will be 0. Right? Firstly, I'm gonna visit all the leaf nodes that are present at 0th time. Now let me start traveling or traversing each node that are inside my queue. So till the time I have at least one leaf node inside my queue, I have to keep on traveling or pruning them, right? This is what the strategy we have utilized. So what we are gonna say, let us take out the leaf nodes one by one. This part is done, and let me pop it out. Now let me visit, if this is my current node, then whatever other node it has an edge. Okay, if suppose this is my current node C and it has an edge towards another edge D, if I prune it off, I am basically removing this edge, and what is happening, its degree count will be going down by 1, and this particular node's degree count again will be going down by 1. Okay, so I need to keep a track firstly that to what other nodes this particular leaf node is having an edge. Okay, so let us first store that somewhere. So I am going to keep a track inside this particular vector of vector C. Okay, how I'm going to keep the track? This particular slot, the 0th slot, will be determining node 0 is having edges to what other nodes, and inside this 0th slot again I will be keeping indivisible list. Suppose that node 0 is having edges towards nodes 1 and 2, so this will be kept as a list here. Okay, so let us try doing that. So once I am here, what I can do is that I can say, okay, inside E of U, okay, dot push underscore back, I can say that V, since U is having an edge towards V, and the same can be said since the entire edge is bidirectional, I can say that, okay, the Vth node has a edge towards the node U. So this is how we can keep it. There is no harm in that. Okay, that's fine. So once I am exploring the edges that my current node is having towards other nodes, so what I will say, okay, let's visit the edges counter E. So I will go there. Our nodes inside this particular edges grid of node I have. Okay, that's what I need to explore. So I will say, okay, firstly, let us decrease the degree count of my current node by 1, and again let us decrease the degree count of the node that this my current node is having towards. Okay, wherever my this node is having an edge towards, okay, and that particular node's degree value will be again going down by 1 since the edge is bidirectional. So I will say that, okay, degree of, so the ith node towards which my current node is having an edge, its degree also will be going down by 1. Now let me check one thing. Okay, if its degree has gone down to 1, I can say that, okay, now this is gonna be my next leaf node, next level's leaf node. If this is so, I am pushing that inside my queue. Okay, the ith node towards which my current node is having an edge, that's pushed towards queue. And what else I need to measure? Any ideas you are having? Okay, at what time I'm gonna visit this, right? So time of this is gonna be just whatever time I have visited my current node, just one more to that. Okay, I have added, and let me keep, okay, what is the latest time in which I can visit any node? Okay, so let that be initially 0, and I will be doing one thing, that, okay, if I will be checking if the current time of the nodes I am exploring. Okay, if that is going greater so than my current latest time. Okay. So I am gonna keep its value inside the latest. So let us change the latest to max of whatever the current value of latest is and whatever the time using which we have visited ith node towards which my current node is having an edge. So this part is done for us. Okay. So hopefully we have visited every node using this loop, and next what we are gonna do, we are gonna keep on my final answer vector, and inside this what I will be storing what nodes I have visited the latest. So let me visit them one by one first and check which nodes are visited at the latest time. So if time of my current node is equal to the latest, I am gonna push them to inside the answer vector and I will be returning them. Okay, finally I will be returning it. Now one thing that we have missed earlier is that I need to declare that okay, the vector of vectors that I am declaring that has initially, let's suppose this is my 2D grid of vectors, so that usually be having will be initialized with empty vectors. Okay, the individual vectors inside each index of the outer vector will be having empty vectors individually, and there will be n slots that needs to be declared, that there will be n minus n indices totally, and each index will be having a total of each index will be having empty vectors individually. So that can be determined by mentioning this n. Another corner case that we have missed is that or that we didn't consider, if suppose the value, or if suppose there is only one node, then that literally has no edges towards it, towards any other node, right? So it has a degree of 0. So what we are going to do here is we can just return, we can declare a vector here, and we can push the only node that we have, that is the 0th node, and can return it from here. No need to do anything for this case mode. Okay, this part is done for us, and let us try now running this program, whether we are able to do it or not. This is the first test cases are accepted for us, and let me try running it. So yeah, there is success, and we have successfully uh, done this problem. And what's the expected time complexity? So see, I am visiting each and every of the node. Each node I am visiting not more than once. So again, this problem can be solved in big O of n time, because every node there are at most n nodes, and we can visit them at most once. So the entire problem can be solved in big O of n time. Okay, so this n is maximally 2 into 10 to the power 4. So that's verily gettable. Okay, with this big O of n approach, the problem is entirely gettable. Thank you for your time.